is the associative property of the union true? Or is this statement true? Now, I'm not quite sure how to say this, so I'm going to do my best. I'm going to say A union with open bracket, B union with C close bracket. Is that equal to open bracket A union with B close bracket union with C? That's a hard thing to say, so I think I'll avoid saying the bracket part, but you should understand what I'm writing. A way to think of this is we're really asking ourselves, is something like 1 plus, or something like A plus B plus C the same as saying A plus B all in a bracket plus C, right? That's kind of what we're saying. Or you can think of it like in terms of multiplication, A times B times C equals to A times B times C, right? And the answer is that, yeah, these aren't exactly what we're asking, but these are akin to basically what this property is that we're testing it for. We're seeing if we have the same thing, the union, does it matter where you put the brackets? Could you really just say A union B union C without needing brackets? Because regardless where you put them, it's all going to be the same, right? So let's think about this. How could we solve this problem? Okay, so because these are our akin examples, we're going to want to think in terms of things like this. So let's try and draw some diagrams to see if this is going to be true. Let's first try checking, because we have 3 sets in this case, we're going to be drawing 3 things. Let's check to see what happens if all 3 of them share some sort of elements. That's going to look something like this. We're going to label this our set A, that our set B, and that our set C. And we're going to ask ourselves, is this the same as what we're going to do on the right-hand side? A, B, C. Okay, so A unioned with open bracket, B unioned with C. How are we going to look at this? Well, first, we're going to look at the brackets, right? We're going to look at B unioned with C. What does that mean? Well, we want all of the elements in B and C. So that's going to mean we're going to want to highlight everything in B, and we're going to highlight everything in C. And then we're going to say, well, because we want this shaded area with A, we want everything in the shaded area here and everything in A, it means we're going to want to also shade everything in A, because we've already shaded this area, right? So let's shade everything in A. So we're basically looking to make sure we include every single element in each set. Is that going to be true in this case? Well, let's have a look. First, we're going to do what we have in the brackets. We're going to look at A unioned with B, which means we're going to want to look at everything in A and B. So we're going to circle all of A, and we're going to circle all of B. And then we're going to say, okay, this is our shaded area, it's our bracket. We want this bracket unioned with our C. So this shaded area, everything in it, and everything in C. So because we're representing everything we want with our shading, we've already shaded our bracketed area. Now let's shade our C, because we want everything in C. That's going to look something like this. And stepping back, yeah, it looks like these two are in fact identical. So it looks like for these cases, it's true. Let's try just 2 more to verify if this is going to be true or not. So what if only 2 of the sets, specifically the set we have out here, share something with the set in the brackets, right? So what is that going to mean? Well, to look at this side, we're going to first take B unioned with C. What is that going to be? Well, it's going to be everything in B. So we're going to highlight everything in B. Unioned with everything in C, we're going to want to highlight everything in C. Fantastic. And we're going to take our shaded areas, and we're going to say, on top of these shaded areas, we want everything in A. So we're going to highlight or shade everything in A. So we're going to shade all of A. Okay, so this is what we're looking to get on the right-hand side. Let's see if we get that using this. So first, we're going to want to take A union B, which means we want everything in A, everything in B. So let's shade both of those in. That's going to look something like this. Okay. Then we want to take our shaded area and say we want everything here and we want everything in C. So we're going to want to circle everything in C. So it looks like this is going to be true for this case as well. Let's try one more example. So in this case, we're looking at our 3 sets and we're saying none of them have anything in common with each other. None of them share any elements together, right? They're all distinct sets. So let's have a look at our left-hand side. We're saying we want to look at everything in B and everything in C. So we're going to want to circle everything in B like so, and we're going to want to circle everything in C like so. And then we're going to say this is our bracketed area. We want everything here and we want everything in our A. So we're going to want to circle all of the elements here. So we're just going to circle or shade, sorry, all of our set A. So this is what we're looking to get on the right-hand side. Let's see if we get that on the right-hand side. First, we're going to look at A union B, which means we're going to want everything in A and B. We're going to want to look at elements and everything. So we're going to circle all of A, and we're going to circle all of B. Fantastic. And then we're going to want this shaded area, this bracketed set we have with these two sets, and we want everything here as well as everything in C. So that means we're going to want to shade everything in C as well. So it's looking like, yes, these are the same. So it looks like for most situations, if not for all of them, this statement is going to be true. So that's enough to have us start writing our proof. So let's go ahead and do that. So to write this proof, we need to understand what we're actually proving. What are we proving? We are proving an equivalence statement, which means that we have to show that the left-hand side is the same as the right-hand side, and the right-hand side is the same as the left-hand side. So how are you going to do that? Well, you need to show the following. You need to prove that the left-hand side, A union B union C, is a subset of the right-hand side, A union B union C. And vice versa. You have to also show that, well, this is true, this A union B close bracket union C is going to be a subset of A union open bracket B union C close bracket. Both of these have to be true. Every element in this set has to be in this set, and then every element in this set has to be in the first set as well. So we have to prove both of these are true to state that this is in fact true. So let's go ahead and do that. This is a for all statement because we're looking at any sets A, B, and C. So what do we start with? We start with a let. We say let A, B, and C be sets. Fantastic. Now we can get into our first case. So our first case is going to be to show that the left-hand side is a subset of the right-hand side. Fantastic. So let's map out our proof. We're going to want to go from A union bracket B union C is going to be a subset of A union B close bracket union C. We're going to want to start here, and our goal is to get to here. And we're going to use the same strategy we've used before. We're going to create a general representative element like X. We're going to say X represents all of the elements in this set. And if we show that because X can be anything here, and if X can be here, because anything here can be here, that means this is going to be a subset of this, right? That's going to be our reasoning here. That because every element here, like X, is going to be in this set as well, that means our set here is going to be a subset of this other set. Okay, a lot of words. Let's get down to problem solving. So how do we get from here to here? Well, first thing we should do is break down what it means for X to be in this set. Well, for X to be in A union open bracket B union C close bracket, it means that X must be an element of B union C, or X must be an element of A. Okay, fantastic. We can break this down a little further. Let's actually switch these around. We can break this down further, and we can say this is like saying X is an element of B, or X is an element of C. So there we go. We've broken down what it means for X to be an element of that set. Now we want to get from here to here. So we somehow need to argue that X can be an element of A union B, and X can be an element of C. Well, what do we notice? Well, we've noticed that we've already got the element of C down, right? We have that right here, that X must be an element of C. Fantastic. Okay. If X is an element of A, then we can probably say that X is an element of A union B, which then, okay, yeah, that's good. Which then means that it can definitely be an element of this set that we were trying to look for. Fantastic. Now we just need to link, so we know what happens if X is in A, we can get it to our goal. We know what happens if X is in C, we can get that to our goal. Now the last thing to do is figure out how to get X, if it's in B, to our goal, so how to get this to our goal. Well, we can use the same argument we used for A, where we say if X is in B, then X is also going to be in A union B, which is just going to mean that X is going to be inside of our goal set. Okay, so this is our logic. Let's write this down into a mathematical sentence. First, we're going to start with supposing our representative element. We're going to say, suppose X is an element of A union B union C. Fantastic. Then we want to do what we did next. Here we're going to break down what it means for X to be an element of this set. It means that then, I'll write it down here. X is an element of B union C, or X is an element of A. Fantastic. Now from here I'm going to immediately jump to A, right? Let's just get that out of the way. So we're going to say if X is an element of A, then X is an element of A union B, so X is an element of A union B union C. Fantastic. Okay, next let's break down what we have here. We're going to say as well as this, for X to be an element of B union C, that means X is an element of B, or X is an element of C. Fantastic. So now we go into these two scenarios. We say if X is an element of B, then X is an element of A union B, so X is an element of A union B union C, right? We're just using the same argument we did for A. Fantastic. Now we just tie the knot with explaining what happens if X is in C. So if X is an element of C, then X is an element by default automatically of A union B union C, right? We can just immediately jump to that because it just needs to be an element of one of these. And we showed that if it's an element of C, then it's going to be an element of this whole set. Fantastic. Now we want to conclude this. So we're going to say full stop, therefore A union open bracket B union C close bracket is a subset of A union B close bracket union C. Fantastic. So we've proven our first case. Now let's go ahead and do the second case. Okay, so our second case we're going to try and prove is that the right-hand side is going to be a subset of the left-hand side, as I've written down here. So what does this mean? We want to start with the right-hand side set and show that any element, for example, y, is going to be also an element of the left-hand side, which means that if every element in our first set is if every element in our first set is also an element in our second set, then the first set here is going to be a subset of the second set. Okay, so how do we do this? Well, let's use the same strategy we did before. Let's break this down. What does it mean for y to be an element of A union B close bracket union C? Well, it means that y must be an element of A union B, or y must be an element of C. Fantastic. What can we do? Well, from here, we can't really jump anywhere yet from here. Okay, let's continue breaking this down. Let's break down what does it mean for y to be an element of A union C. Well, it means y is an element of A, or y is an element of B. Okay, fantastic. So we've kind of got to the similar points we did in the first case. Now we want to get from here to our goal. How can we show that y is at least an element? Well, we've already got the A part covered, right? We've shown that y can be an element of A, which means that it automatically, oh, I don't want to circle this part. I meant to circle the other part. So if this is true, then we can immediately say that goes here. Fantastic. Okay, so we've covered if y is in A. Obviously, it's going to be in the set A unioned with whatever. Okay, now we want to say, what if y is B? Well, if y is in B, we can say that y would definitely be in the set B union C. And similarly for C, if y is in C, then y is definitely going to be in the set B union C. And both of these are going to lead us to our other side of the goal we want to get to. Okay, so this is going to be our sketch. Now let's try and put this into words. So the first thing we're going to start with is by writing down our representative variable. So we're going to say, suppose y is an element of A union B close bracket union C. Fantastic. Now we want to break down what that means. We say then, in fact, I won't use this. I will use the space below. We'll say then y must be an element of A union B, or y is an element of C. Fantastic. Okay. Unlike the first case, I don't want to just use our y as an element of one set yet. So I'll save the. Actually, no, I'll do that now. I'll stick with that pattern. So we'll first look at when y is an element of one set, in this case C. So we're going to say if y is an element of C, then y is an element of B union C. So y is going to be inherently, I'm going to sit down to keep my writing straight, y is going to be inherently an element of A union B union C. Fantastic. Okay. Next, we're going to want to look at our case where y is a union of y is an element of A union B. We're going to want to break this down like we did up here. So we're going to say if y is an element of A union B, then y is an element of A or y is an element of B. Fantastic. Then we're going to say if y is an element of A, then y is an element of A union B union C, close bracket. Fantastic. And we'll say, and if y is an element of B, then y is an element of B union C, so y is an element of A union B union C. There we go. Okay, so that's enough to show us that the element y is always going to be not just in this set, but it's also going to be in the set we're looking to be a subset of. So we can now conclude that, therefore, we can say A union B, all in a bracket, union C is a subset of A union open bracket B union C, close bracket. Fantastic. So we've proven both of our cases to be true. Now we're going to want to show, we don't want to show anything now. Now we can just conclude our statement, right? We can say that overall, since A union open bracket B union C is a subset of A union B close bracket union C, and the other way around, A union B all in a bracket union C is a subset of A union open bracket B union C. Did I say that right? Yes, I did. Okay. A little shabby, but this is a lot of writing and a lot of talking. So since this is true, we could say that then A union open bracket B union C is equal to A union B all in a bracket union C. Fantastic. We have now proven exactly the statement that we wanted to prove to be true.